All right, good afternoon. My name is Han. Today I'm going to talk about PerfLerner. PerfLerner is a framework that can learn from performance bugs to understand and generate performance test frames. We have published this work in the 13th International Conference on Automated Software Engineering. Also working on this project is my advisor, Dr. Ting Yu, and our collaborator, Dr. David Rowe. So software performance is crucial as we use software every day, and we normally struggle if the software does not perform. So I'm not sure how you feel about this, but if I say this and it doesn't go away anytime soon, my blood pressure will go up. When I'm talking about performance bugs, I'm referring to the bugs that could cause severe performance degradation for some program input. And also, this normally leads to very poor user experiences. For instance, the code snippet that we're looking right now is about a Apache performance bug. So what happens is that because of the faulty code, the restore process of Apache takes minutes instead of seconds. So one of the many ways to guarantee the quality of software performance is through testing. And performance testing, like many other testing techniques, involves with the test inputs and the test articles. For here, we normally refer data inputs configurations as the test inputs, whereas the expected performance measure will be used as the test articles. And one of the widely used methods to pinpoint the performance threshold is by using the profiling method, such as the *2 on Linux. So profiling method relies on the existing test inputs, and they normally use the execution as the test article. But the problem with this type of method is that they rely on the existing test inputs, which may not trigger the performance bugs. Others have been focusing on generating performance test cases, such as Burnham et al. They have introduced a method that could increase the workload values. Shin et al. They proposed a method that used a search-based method to explore the combinatorial space of the test inputs. However, even though those methods works great, but there are some limitations. For instance, for the first method, it normally ignores the combinatorial effects of different input parameters. And for instance, in the Apache bug 52914, in order to trigger this performance bug, you will need both configuration options. And for the second method, the problem is that the number of test inputs generated from the extensive method can normally be inefficient. Because many of the parameters may just not relevant to the performance of the application. For instance, in Apache Server, we have more than 600 configurations and 8 other types of data inputs. And the combination of these parameters can go well beyond millions, and many of which are not relevant to performance issues. So the insight here is that we want to focus on the test input generation that are relevant to the application's performance. So since our work is heavily reliant on bug reports, I'd like to give you a taste of what the bug report, performance bug report look like. So here we're looking at a MySQL database bug report. What this bug says is that when the user is trying to update the index column, it takes longer than before. And this is true when the configuration option, DB fill factor is set to the default value, which is 100. So if I were to ask to write a test case for this performance bug, this is something that I will come up with. And here, update is the command. Command is something that we refer to as an action to execute a functional unit. And along with the command, we have what is referred to as the input parameters. Full is the name of the column, and the DB field factor is the name of the configuration option. To design our framework, we have conducted a thorough performance bug study. Specifically, we have studied 3 open source and popular projects: Apache Web Server, MySQL Database Server, and Firefox Browser. To collect our data, we use the performance keywords and search against the bug reports to get a total number of 1,383 performance bugs. And all of this pool, we have randomly set 100 performance bugs for each project. And we identify 45 commands and 2,413 configuration options, as well as 30 data inputs. So through our study, we have found that the majority of the study performance bugs involve more than 1 input parameters. And about roughly half of the performance bugs are related to configuration options, and only a quarter of those bugs require the specific workload values to manifest. And all of the 2,000 configuration bugs, only a small portion, 5%, that are relevant to the performance issues. Interestingly, more than half of them appear more than just one time. So the lessons that we have here is that, so the bug reports are related to a very specific set of vocabularies that's related to the commands and input parameters. Also, the combinatorial effects among the input parameters should be considered in the performance testing. And we have also noticed that only a small subset of the input parameters tend to affect the performance of applications. And lastly, we should give priority to commands and input parameters that appear more frequently, as they have a much better chance to expose the performance bugs. For this project, we have designed a tool, PerfLerner, that can automatically extract the performance-related commands and input parameters from the bug report and generate test frames, which I will talk about in details in the next slide. And also, we have implemented PerfLerner and conduct empirical study to evaluate its effectiveness and efficiency in terms of generating test frames as well as to detect root performance bugs. So the test frame was first introduced by Austrian in 1988 in the category partition method with the test specification language. So this technique defines the combination of the program input parameters and its environment factors. For each combination, it represents a set of data inputs that can be later converted to the actual test cases. And in our case, a performance test frame would consist of 3 input categories. There are commands, configuration options, and data inputs. So what we normally see a test frame will be something like this. Okay, now that we have taken care of the basic concepts, I'd like to move on to the overall approach of PerfLerner. So the first part of this approach concerns with the test input extraction. First, the approach takes the bug report as well as the frame element database as the input. Here, the frame element database specifies what tokens can be used to refer to commands, configuration options, and database inputs. And of course, they are application specific. and the inputs will be further passed along to the framework, which will use information retrieval as well as linguistic pattern matching to extract the test frame elements. So naturally, we would think that in order to get all those test frame elements, why can't we just use a grep-like search method? However, it doesn't always work. For instance, for the free elements that share the same word, like the one in this Apache bug, where the keyword timeout can be used both as the command or as the configuration option name. There's no way that the search method know how to distinguish the two. And also, the search method could result in false positives. As we have seen in the same bug that both start and request appear in this bug, and request is the actual command that triggers the bug. However, start, if we use the search method, actually counts more than request, and it will hence rank higher than the actual command. So to take on these challenges, our solution is to provide a series of patterns for commands, data inputs, and the workloads. And for configuration options, we use the information retrieval, which I will detail in the next few slides. Okay, so for the command extraction, we observe that a command normally appear in the same, normally appear with the bug symptom in the same sentence. So for instance, if we look at this bug, here the sentence says, I could reproduce the 100% CPU with the post request. Here, the 100% CPU is the symptom and the post request is the command. So if we could increase the search accuracy for the command by narrowing down to the sentence that contains the bug symptoms. Likewise, for the data input, we observe that data inputs coexist with commands. For instance, this sentence starts with the command update and followed by the preposition to, and then followed by the data input column. And from the testing, we always care about workload because workloads are known to be a major factor to lead to performance problems. So the way that we pinpoint the workloads is by using linguistic patterns such like this. So in this pattern, this sentence starts with the data input file and followed by the verb contains. And afterward, it describes the content of the file, which is a very long line. Another frequently used pattern would be to pinpoint the sentences that contains the name of the benchmark tools, because normally in the bug report, people will use performance benchmark tools to simulate the workload. However, unlike the commands and other input parameters, configuration option is a different animal. So first, not every bug report mentions the name of the configuration explicitly. So if it's not there, you cannot search it. So someone might think about we can use the information retrieval techniques, such as the naive way would be to split the name of the configuration options and use those tokens and calculate the quotient similarity scores against the performance bugs. It works in some cases. However, when multiple configuration options share the same tokens, it will end up ranking the same. It will end up ranking the different configuration options at the same place. So to take on that problem, we leverage the configuration option manuals to bridge the lexical gap. Okay, so that concludes the input extraction part, and now let's move on to the test frame generation. So for the test frame generation, first we do is from the previous step, we rank each element according to its appearance frequency. And for configuration options, we rank the items by using the cosine similarity scores. So once we have the rankings, we introduce the strengths file, which in the strengths file it specifies the top n ranked frame elements that will be participating in generating the test frames. And the values used here are guided by our previous bug studies. And also we use the constraint file, which specifies what elements can go with what other elements. The purpose of this constraint file is to reduce the number of invalid input element combinations. And in the end, we got a list of test frames. And lastly, let's talk about the test cases. So for test case generation, the first thing we do is we iteratively select the test frames from the prioritized list that generated from the previous step. And then we convert the test frames into an XML file, of which the structure is known to the underlying test case generation engine. And it is totally up to the test case generation tool to determine what concrete values should be associated with each input categories. To evaluate our framework PerfLerner, we have the following. We have conducted an empirical study, and we're trying to answer the following research questions. So first, we want to see how accurate is PerfLerner at detecting components blocks triggering frame elements and the workload. Research question 2 talks about the effectiveness and efficiency of PerfLerner at generating performance test frames. And lastly, we want to see whether PerfLerner can help existing performance test case generating tools to generate better test cases to detect performance bugs. To answer the first research question, we use the search-based method as our baseline method. And to evaluate the effectiveness of ranking, we use 2 metrics. The first one is the top-end success rate, and the other one is the mean average procedure. The top-end success rate goes like this. If 20 out of 100 performance bugs reports run the run choose correctly, then the success rate is 20%. And for the MAP, let's assume it handles the case when the query would result in multiple documents. For instance, for a given bug report, there might be 2 configurations that are related to this bug report in order to trigger the performance bug. So let's say that we have 2 techniques, and the first technique will rank the first configuration option at the first place, and the second configuration option at the second place. And for the second technique, it ranks the second configuration option at the third place. And accordingly, we can calculate the max score for each technique. And obviously, the first one is better because both of the configuration options should be run at the top 2 places. And to answer the second research question, because we cannot find an existing approach that generates the performance test frames, so instead we use the combinatorial testing. So what differs the CT method with PerfLerner is that First, the city method does not analyze the bug report, nor does it run the frame elements. Also, the workload is randomly assigned to the frame elements. And to measure the effectiveness, we manually derive the ground truth test frames for the performance bugs under evaluation, and we monitor under which iteration each technique will generate the ground truth test frame. And for the last research question, since PerfLerner is orthogonal to the existing performance test case, generation methods, we combine PerfLerner with GA-Prof, which is a tool that generates performance test cases, and see if this can help GA-Prof to better detect performance bugs. And we evaluate 10 performance bugs that we know beforehand how to reproduce. And also we record the time that it takes to find the performance bug. So just to remind you that we have conducted the empirical study, and there are 3 projects. And this table shows the result for the first research question. Here, for command and data inputs, we compare PerfLerner with a search-based method. And for the configuration options, we also use the naive information retrieval method to compare with PerfLerner. And for the accuracy of workload, we use a random method which will assign workload to test frame elements randomly. And our result shows that both the successful rate and MAP scores are higher in each category of all programs. So that means that the natural language processing and information retrieval techniques used by PerfLerner is effective in boosting the ranking accuracy. So this table shows the result for the research question 2. In the second column here, it shows the number of constraints that we use in each application to reduce the number of test input combinations. And here, the space column indicates the number of the space of the combination of the test frame elements. The comp average shows the number of iterations that each method takes to generate the ground truth test frame. So as we can see, when we compare PerfLerner with the combinatorial testing method, both numbers are much lower. So this shows that PerfLerner is more cost-effective at generating performance test frames than the traditional combinatorial testing approach. And for the last research question, for effectiveness, it shows that the method that, the default method, the GA-Prof, misses 10 out of 10 performance bugs, whereas the PerfLerner captures 7 out of 10 bugs. As for the efficiency, 10 out of 10 bugs ran out of time for the baseline method, GA-Prof. And on average, PerfLerner takes about 10 hours to detect the performance bug, and it uses much less iterations to do so. So it shows that PerfLerner can potentially enhance the existing performance testing generation tools. To sum up, in this work, we have conducted a bug study of 300 performance bugs also design and implement PerfLerner, and lastly, we have evaluated on the efficiency and the effectiveness of the framework. And that is all I have today. I can answer a few questions if you have any. Yes, sir.
So what are the characteristics of a software system that would make PerfLerner a useful tool to use to generate these tests? You applied 3 cases, but how does it generalize? What sort of a lesson can I take out of it? When I would use it?
Right. So there are some limitations, such as, because our method is based on the bug reports. So for some of the newer projects, they may not even have that. So there's no way that we can generate test frames for those type of things. And also, our work is pretty much focusing on those performance projects that are highly configurable, which means that the configuration options, they play an important part. So if the subject project does not have a lot of configuration options, we might fall short on that as well. Yes, sir.
You'll extract some information from the lab report, right? Like what kind of so basically you summarize some patterns.
Correct.
Yeah. Is there any risk of poor fitting this pattern? Did you provide the lab to size and look for a cross validation?
Yes, there's always a chance that the method won't work. However, in this study, we haven't tried to generate the. As a matter of fact, even though we haven't tried to use the patterns across projects, but our assumption is that for these types of applications, the patterns that we define is not unique to a certain project. So in a way, they're kind of universal. So does that answer your question?
Well, thank you very much. And this concludes our first of our series of great Keeping Current seminars. See you next week. Thank you.